Hi, NA Physics, it's Mr. Neff. Today let's talk about the wave-particle duality of light. But before we do, did you hear about the crime that happened in the parking garage? I'll tell you about that at the end of the video. People have been asking for a long time, what is light? What is it really? And in the 16 and 1700s, Isaac Newton came up with a theory that said that light is a stream of little particles. He called that the corpuscular theory of light. Corpuscles are little particles. It makes some sense too, because think about the way particles behave when they reflect. Say you were playing pool and you hit the cue ball along this angle. Well, here's your angle of incidence. And you can very easily predict what the angle of reflection is going to be. It's going to be the same. You can use those little triangles or those little diamonds, 3 of them in between each hole, to tell what the angle is going to be. You can just do some similar triangles and you can very easily predict the angles that they reflect. Well, light acts like that too. Remember this simulator that we've used many times now from our friends over at PhET, and it shows that interface between 2 substances. And look, if I turn the laser beam on, I get an angle of incidence and an angle of reflection, and we've seen it before. We'll see it one more time. They're the same thing. And so in the end, light behaves like a particle, it reflects like a particle, so maybe it is a particle, thinks Newton. But now here's a different simulator from our friends at PhET. And this shows a water wave generator, and those water waves are going to come over and they're going to be obstructed some obstacles. So there's a spot here where the waves can get through, there's a spot here where the waves can get through, and when they do, you'll see them come over here onto the right side of the simulator. So we turn this on. And see what's happening. You get waves over here on the left side, and then they encounter these obstacles and you get this interference pattern happening over here. I can show you the interference pattern. I can show you what the waves look like, the amplitude of the waves look like before. That's the light gray one going up and down, basically as tall as the chart is. And then over here, I can put this other one, and now if I put it right there, nobody's very impressed by that. They say, well, those waves are just going right through. But if I put it down here where there's right behind this obstruction, you might say, oh, look at that. How is it that is producing such a large amplitude? Its own amplitude, it's almost as big as what we had over here. And it's happening because of interference. So this spot, the waves from here are going up this way, and the waves from here are going over that way. And I put that pretty much smack dab in the middle so that the path length between those two is about the same. Anyhow, we're seeing interference, and so what you see from the dark graph over here is the sum total of the 2 waves' amplitudes. Now, if I move this over just a little bit, you'll see right in about here, in a spot where you wouldn't think, now I'm getting, even though it's right in front of the opening, I'm getting an amplitude that's not nearly as much, because you can kind of see this is a place where the 2 are going to be out of phase. Don't look at the 2 graphs out of phase, but the wave that's coming from here and the wave that's coming from here are going to be out of phase. Now, a scientist named Christian Huygens came after Newton and said that waves work because any spot on a wave is the source for the next spot on the wave. That's since then been called Huygens' principle. And so we're saying that this space is sort of becoming a wave source, this space is becoming a wave source, and so those 2 are interfering at this spot. Okay, but I thought this was supposed to be a video about light. Well, it is. And I'm going to change this over to light. And so now this is a light generator. And this is good. We're super zoomed in, because you're going to see these light waves like plane waves coming across, just sort of like you saw before. And here they go. Now, of course, I could change the frequency and so forth. Now, because this is very, very high frequency, these are going up and down like crazy. So if it's okay with you, I'm going to put this in slow motion. And now I get the same kind of thing. If light was a particle, I should get particles occupying this space right here, right across, almost a right angle to the obstacle. But I should have nothing going on up here. But I do. And if I change this to 2 slits, now you can really see I should get nothing right here. This is, imagine if this is a flashlight and there's 2 little holes. I should just get 2 little images of the holes over here. And definitely darkness behind. That's not what I'm getting. You see, I'm getting these waves are filling in this space behind here. I'm getting these places to be places where the waves are reaching. And so this is light acting very wave-like and not nearly as particle-like. Again, if they were acting like particles, I'd expect to see a path of particles as big as the slit all the way over. And this would be darkness, this would be darkness back here, this would be darkness here, but that's not what I'm getting. Not just that, but now if I take this and I move this just slightly to the side, you can see I'm trying to hit that spot that's kind of a dead zone. And there, maybe there. Look, I'm getting not very much amplitude versus if I go just a little bit to the side, now look, I'm getting a lot more amplitude. You can see that there's interference going on here. And what kind of things interfere? Waves interfere. So as I say, Huygens said, hey, you can see waves interfere and light interferes. So light must be a wave. And consequently, when Huygens came out with this, the world started to say, well, I know about the reflection side of it, but the interference part is very, very compelling. So we're going with light is a wave. And so that's where we were for a little while of time. So for a century, century and a half, we said light was a wave. But then in 1839, a Frenchman, Edmond Becquerel, noticed a thing that when you shine light on a metal, you can get the metal to give up its electrons. Today we call this idea the photoelectric effect. I have a nice simulator of this. Okay, look at this. So here's a flashlight that you can set any amount of intensity you want or set any color that you want, even including infrared and ultraviolet light. It's going to shine on this thin piece of metal. You see this thin piece of metal over here on the right side of this support? That's called a target metal. And you can make the target metal a bunch of different things, whatever you'd like here. We're just going to leave it on sodium. Okay, so now if you shine a light on that target metal, you can get the target metal to give up electrons. And because they are ejected by light, we call them photoelectrons. But they're not special. They're just electrons that were ejected from the metal because of light. Okay, so I'm going to turn this on, turn on some red light. And maybe I'll put it on like 53%. And nothing's happening. Maybe I better turn it up all the way. 100%. Now, maybe there just hasn't been enough energy delivered yet. That's got to be the reason. And I can tell you, I'm not acting. There really hasn't been enough energy delivered to get the electrons off of there. So what if we wait a while? Because if light's a wave, you just give a wave long enough and it'll deliver more and more and more energy. So what if we just wait a while? Still not working. I don't want to waste your time. I'm going to try something else. I'm going to try to take this color and move it up some. So now I have a real good red color. Nothing. Some orange. Yellow. How about green? Oh! There's some photoelectrons. Now wait a minute. Green's working. But orange does not. But yellow does not. Green works. What about blue? Ooh, even better. Darker blue. Yeah. Violet. Oh, baby, look at that. ultraviolet. You won't see it, but oh, look at that. Lots of photoelectrons coming off of there. So Becquerel noticed this, but it took a little while for Einstein to finally say, you know what? This is happening because of those things actually act particle-like. Einstein said that each one of them, each bit of light is quantified, meaning that it comes in a little bundle. He said that the bundle is going to have an amount of energy that's proportional to the frequency. And if you notice, the higher frequencies were effective and the lower frequencies were not. And so he said that if you think of the light in little bundles, little particles, little pieces, you say those pieces are either effective because they're high enough frequency or they're not effective. And so this not only is the basis for a solar panel, but this is also a reason why we say that sometimes light acts particle-like and sometimes light acts wave-like. And so we're gonna have to leave it at that. What is light? I don't really know if I have a good answer to that, but I will say that at certain times it acts very wave-like, and at other times it acts very particle-like. And so Einstein said that it seems like we must use sometimes the one description and sometimes the other description because neither one of those really fully fit what light is. All right, well, I hope that clears up some of the misconception of the wave-particle duality of light. And before we leave, did you hear about that crime in the parking garage? It was wrong on so many levels.